speak to the pulpit.
Nah. Welcome everyone to the Newport Historical Society. I'm Ruth Taylor, I'm the Executive Director here, and I'm delighted to see you all. I'd like to thank our sponsors for tonight's event, Greenvale Vineyards and Whispering Angel Rosé. I'd also like to thank our co-sponsor for this event, and actually this is our second co-sponsor event this week. We're setting a tradition, the Newport Restoration Foundation, and Kelsey Mullen of the Newport Restoration Foundation would like to say a word.
Hi there, I'm Kelsey Mullen and I serve as the Public Programs Manager for the Newport Restoration Foundation, and it truly is our pleasure to be here with the Historical Society today. As many of you are already aware, since 2014 we have been working on an initiative called Keeping History Above Water, which looks at the intersection of climate impact and cultural heritage. This has been a tremendous learning experience for us, but what we have taken away in our time on this project is that interdisciplinary, interorganizational collaboration is really key to addressing some of these very big questions that we are all increasingly facing on a day-to-day or week-to-week basis. So thank you to the Historical Society for hosting this today, and we are excited for the lecture to come.
So I wanted to say something about our speaker and how he got here. So first I need to thank Elizabeth Leatherman for bringing Jeff Donnelly to us. I guess she heard you speak in Florida, and you were remarkable. So our expectations are high. Jeff is a senior scientist at the Woods Hole Oceanographic Institution. He grew up in Massachusetts and has spent much of his life here in New England. He earned a bachelor's degree in earth science from the University of Massachusetts, my alma mater as well, and a master's in coastal and watershed systems from Yale, and a doctorate in coastal geology from Brown. Jeez.
Wow. That covers all 3 states.
Yeah, pretty much. Much of his work involves piecing together New England's climate in the recent past. There's the Historical Society connection. His overarching goal is to understand how changes in the climate system have altered terrestrial and coastal systems, and vice versa, and so improve our ability to project how coastal landforms and embayments will respond to future changes. From 2004 to 2006, he was a joint fellow of the Coastal Ocean Institute and the Ocean and Climate Change Institute at Woods Hole. So please join me in welcoming Jeff Donnelly.
Good evening, everyone. I'm going to make a quick plug for the organization that I've worked for now for 18 years, the Woods Hole Oceanographic Institution. It's an amazing place. We've basically taken over a little fishing village on Cape Cod and made it a scientific mecca for the entire world. People come from all over and work in Woods Hole. It's driven by, intellectually driven by about 130 scientists and engineers who are sort of focused on all aspects of ocean science, and importantly, looking at how it sort of benefits society. And my little piece of this, right, is one of the things that I'm sort of most interested in studying are sort of the climate impacts that we are going to face day in, day out, and mostly related to hurricanes and sea level rise. And I should point out that the other piece of this that's critical is us. We're obviously the other part of the system that's sort of interfacing with the natural system. Oops, my direction. All right, so as a geologist, I'm going to take you on a little trip through time, probably a little deeper in time than the Historical Society usually goes. We're going to go 400,000 years into the past. This is a record of CO2 in the atmosphere going back 400,000 years. And the reason we have this record is because air bubbles are preserved in the ice sheets in both Greenland and Antarctica. And by drilling those ice sheets, we're able to basically figure out what the atmospheric composition has been like for 400,000 years. You can see that there's been a sort of cyclic fluctuation between about somewhere around 200 parts per million and 300 parts per million over the last 400,000 years. And these are corresponding to the glacial and interglacial cycles over that interval.
Is that consistent throughout the world though?
Yeah, so the atmospheric CO2 is really well mixed, and so it's a very uniform signal across the globe. In the year I was born, 1966, we were already at 320 parts per million of CO2 in the atmosphere. So we were already, by 1966, well above anything we've experienced over the last 400,000 years. Today we're at 408 parts per million, so more than double. And the projections for the future, if we stay on this trajectory in terms of our current carbon economy, by 2100, we're going to be looking at over 900 parts per million CO2 in the atmosphere. And that's going to correspond to a global warming of about 6.5 degrees Fahrenheit. And even if we manage the political will to do something, for example, the COP21 Paris Accord that many of you have probably heard about from a couple of years ago, even if we sort of manage to sort of hit those goals, we're still looking at something closer to 650 to 700 parts per million CO2 in the atmosphere by 2100, which would be something like a 4-degree Fahrenheit warming.
Jeff?
Yes?
Do you encourage questions during your talk, or should we hold on?
We're going to have time for discussion after. If it's a question about clarification, let's go for it. Because if I said something that people don't understand, let's make sure they understand it.
Well, I forget a lot, so I'm just wondering if at some point the additional parts per million makes the air we breathe toxic.
We are not approaching that here. That's a lot more CO2. There's a lot of air out there. The problem is the thermal physics that are going on trapping the warmth at these levels. So we don't have to worry about that. So here's a snapshot of what the world might look like going into the future. And again, this is looking out to the end of this century. So it's going out beyond which we're going to experience, but what our children and grandchildren might experience. And this is a climate model result. There's many climate models out there. They all tell us the same thing because the physics is the same. We know that putting greenhouse gases in the atmosphere results in warming. It just does. It's physics. It's not political. It just happens. On the left here, if we were to do something like that Paris Accord, we'd be looking at something like this. If we go with sort of business as usual, we look something like this. And the reason I show this is that even if we muster the political will to do something, we're still going to be dealing with a warming world. And there's a lot of impacts from that we need to sort of wrestle with. And the one that I'm going to focus on tonight is how will this warming, regardless of whether it's this warming or this warming, how is that going to impact sea level rise and hurricane activity? So there's been a bunch of exercises trying to forecast future hurricane activity in this warming climate. This is just a couple of snapshots from a somewhat recent attempt at that. And it's by Terry Emanuel at MIT. And one of the reasons I like to show this is because he's not just focused out at the end of this century. So the climatologists like to sort of think about, okay, let's think about, we're looking for a big signal, so let's look at all the way to the end of the century and see what it looks like. What Kerry did here is actually measured it every decade, or modeled it every decade. And so the first thing I like to point out is, so here he's basically modeling in the historic interval, which we've all experienced, and this is the sort of future projection going out. And what I'd like to point out is that it's not a 2100 problem. It's a problem we're likely to experience in the next couple of decades. So this big ramp up, and this is annual frequency of tropical cyclones globally, all is occurring over the next few decades that we are likely to actually experience. The other figure from this paper that I like to show is this one, and this is the spatial fingerprint of that increase in activity. And you can see that there are some winners and losers here. For example, the western North Pacific is the hotspot. There's the most increase in tropical cyclone activity there. So if you're thinking of buying a coastal property, maybe not the western North Pacific. But the western North Atlantic is also somewhat a hotspot for increased activity in this particular modeling result. The southern hemisphere actually sees very little increase or no increase. And so it's not just everybody's going to get more hurricanes or tropical cyclones. There's going to be this regionality to it. There's going to be winners and losers. This is another one I like to show. This is an exercise that was done by some folks down at the Geophysical Fluid Dynamics Lab at Princeton. And they're modeling a scenario in which we actually do something about our CO2 emissions. So this is sort of the best case scenario. And they're looking at just the biggest storms, the category 4 and 5 storms globally. The top panel here is the number of category 4 and 5 storms that they modeled in present day climate. And then they go to the end again into this century and model it again. And there's a significant increase. Globally, there's a 28% increase in the the biggest storms, the most intense storms, the category 4s and 5s. And in the Atlantic, there's a 42% increase. So even if we manage to do something, we're still wrestling potentially with this problem of increased hurricane activity, particularly the more intense storms. Now, there's also regionality here too. You see there's increase here and increase here in the western North Pacific and western North Atlantic, like that other study showed. But there's actually a decrease in hurricane or tropical cyclone activity in the South Pacific. So you get many more today versus in the future. So again, there's sort of winners and losers. So maybe the coastal property might go in the South Pacific.
Could you explain that, please? Why? Why are so many more in the North Hemisphere?
It basically comes down to the distribution of heat and how it gets sort of, if you remember, most of the warming in that first, the global red plots I was showing is happening in the Northern Hemisphere. So that's what you're getting, you're sort of supercharging the system by increasing the warming in the Northern Hemisphere. And the reason that happens is because there's more land there. The water in the Southern Hemisphere, there's much more of it, and it's able to absorb more of the heat. Right? And so it's more, the atmosphere and the ocean is more and more in the Northern Hemisphere. So of course we're no stranger to hurricanes here. It's not just something that's happening because of global warming, it's been happening all along. The most recent one we had here was Hurricane Bob. It made landfall right here in Newport. It was a Category 2 storm at landfall. We were lucky that it largely was low tide or medium tide, so it wasn't nearly as bad as it could have been. But there are many other examples that I'll show a couple of sort of the bigger ones through the historic era. And so one of them that many of you have probably heard about is the 1938 hurricane. And I'm going to show a few of these graphics in a row. What this is a simulation of the storm surge. These colors are basically water being pushed up onto the shore by the storm. Those flags, those multicolored flags, are the actual wind field of the storm. It comes up, makes landfall in Long Island, and then goes up into Connecticut and into northern New England. The green are tropical storm force, the red are hurricane force, and the black are Category 3 or greater winds. So this is a Category 3 storm, much more intense than Hurricane Bob, and it results in massive storm surge all along the southeastern New England coast. And in particular, there's focusing that occurs up in Buzzards Bay and Narragansett Bay, because you've got a sort of south-facing narrowing embayments. The water gets piled up in there, it's got no place to go but up. Before this, and you can sort of excuse us for not sort of being prepared for 1938, because it's been a long time since we had one like it. You have to go all the way back to 1815 before there was another similar storm to 1938. It makes landfall almost in the same spot, just a little bit further to the east, and it goes a little bit more to the northeast, and comes sort of right up the Connecticut-Rhode Island border. Again, lots of storm surge here in Narragansett Bay and in Buzzards Bay. And then there's another one that happens, it's probably the most intense, or at least it's the most intense for southeastern New England, and occurs just after European settlement. So in 1635, the only Europeans on the landscape are the ones in Plymouth and Boston. Right? So, and it just happens to pass right between those two places. And because of that, we have an immense amount of information from it. So Winthrop and Bradford, the governors at the time, wrote very extensive entries in their diaries, and lots of other letters and things like that sort of describe what happened in this particular event. It's similar in intensity to that 1938 storm, probably. It sort of makes a brush of Long Island, and then, as I said, comes right between Plymouth and Boston. It causes the storm surge to rise 20 feet in Buzzards Bay. This is sort of a blow up here. You can see at the end it's going to show the maximum storm surge that was attained during the event. And here's the scale of 20 feet. So you can see Marion, Mattapoisett, Wareham, Bourne, 20 feet of storm surge there. And then there's some descriptions that they provide that I included a few up here. So Winthrop, who's the governor of the Mass Bay colony, The tide rose at Narragansett 1,400 feet higher than ordinary and drowned 8 Indians flying from their wigwams. Bradford at Plymouth. A mighty storm of wind and rain as none living in these parts either English or Indians ever saw. It caused the sea to swell to the south wind in this place about 20 feet right up and down, and made many of the Indians to climb the trees for their safety. And this last one I find pretty impressive. It says it blew down many hundred thousands of trees, turning up the stronger by the roots and breaking the higher pine trees off in the middle. So, I'm going to talk a little bit about sort of the role we're playing in all this. This is U.S. hurricane damage going back to 1900. And you can see, and it's all in 2005 dollars. So not that much damage until we get to the later part of the 20th century, basically. And this open one here it's open because it's last year, and we're still sort of assessing what the damage was last year from the 3 storms we experienced, but it's over $200 billion last year. Now many, when they first sort of started looking at this data, said, oh my gosh, the storms are getting worse, right? But in fact, that's not necessarily what's going on. What's going on is that we are putting ourselves and our stuff in harm's way, right? And so what I'm going to show you is sort of what the impact of us sort of getting much wealthier and much more populous and moving to the coast has been. And this is based on work that a colleague of mine, Roger Filkey Jr., has done over the years. So the first thing I want to point out is that there's been huge coastal population growth. Here's coastal population, or just the Rhode Island population, going back to the 17th century. And you can see that since the middle part of the 19th century, there's been a dramatic increase in population in Rhode Island to now over 1 million people. And this has been mirrored all over the eastern seaboard of the United States. So if we take into account this increase in population at the coast and the increase in wealth that came with that, you get a very different picture. So this is basically going right back to that same plot. Here's sort of the damage in 2005 dollars. But what if these older storms were to come back and hit today, which is effectively what this Pilkey analysis is sort of asking. So if the 1926 Miami hurricane hit today, what would the damage likely be? And you get a very different story. It looks more like this, right? So there's not this big ramp up. And it's not that the hurricanes are getting stronger. It's that we, over the course of the 20th century, put ourselves and a lot of our stuff in harm's way over that interval. And the next slide will show some of the highlights here. So this first one is the infamous 1900 Galveston hurricane, which caused over 5,000 lives lost. Then we had, unfortunately, another one 15 years later. Here's that 1926 Miami. So just one storm going into Miami is almost as much damage as we experienced last year with 3 storms going into Texas, Puerto Rico, and Florida. And a few others. Here's that 1938 hurricane. If that were to come back today, we'd be looking at something like a $50 billion event. Here's Hurricane Andrew in 1992. The 2004 season. The 2005 season includes Katrina. Here's Sandy, which wasn't even a hurricane when it made landfall. It was a hybrid storm that was roughly strong tropical cyclone or strong tropical storm strength, just below sort of hurricane strength winds. Yet it still caused about $70 billion in damage. On top of all that, we've got sea level rising, right? So not only have we put many more people at the coast and more of their stuff, but sea level rising. And we know this. We measured it. The earlier part of this record, going back to 1700, is done with some proxy records. Salt marshes, for example, are great recorders about sea levels change because they have a very narrow ecological tolerance for flooding. And so as they sort of accumulate through time, they provide a record of how the sea levels change. But then up in here, we actually have tide gauges that have been installed all over the world, actually measuring how sea levels change. And you can see that it sort of flatlined back here, and then it starts to increase here in the later part of the 19th century, and continues to rise through the 20th century. And then these two are the predictions out in the future. The red is the sort of business as usual trajectory. The blue is we try to do something and cut back the emissions and reduce the warming. And so just based on these projections, and this is from the Intergovernmental Panel on Climate Change report of a few years ago, they're looking at somewhere between 2 and 4 feet of sea level rise by 2100. This was really conservative and actually really controversial in the scientific community when it came out. because it didn't include something that we thought was really important, and that is the ice sheets. This was just looking, at the time, they didn't have a really good handle on what the ice sheets were doing, and thought about it back and forth and decided, well, we'll just leave it out, right? So it turns out, this is a minimum estimate. If we start looking at what the ice sheets might contribute, the story gets even worse. And I'm going to show, there's a recent paper by Canto and Pollard, who Canto is based at UMass, who actually are trying to model this just for Antarctica. We're not even thinking about Greenland. We just have this estimate from Antarctica. And this is just one of the figures from their paper. And not to get too crazy, I mean, don't get too scared. We're looking out to 2500 AD here, so this is way beyond 2100. But in their modeling exercise, looking at these various emission scenarios and the warming that you'd expect with it, they're looking at something like 51 feet in a business one as usual by 2500. Now that's a long way off and not something we're not necessarily even equipped to start thinking about planning for. But if you look at just what we might expect over the next century, just from Antarctica, this doesn't include the other components like the thermal expansion that occurs when the ocean warms. There's another 3 feet that we could potentially get out of Antarctica of melting. So you have to add that to that other estimate. And that's what we're going to do here. So here's that last IPCC report estimate of somewhere between 2 and 4 feet. If you include just this estimate from Antarctica, we might be looking at something more like 5 to 8 feet of sea level rise. That's a big difference. And that, in terms of managing that, is a huge, huge challenge. So now I'm going to move on to something providing a longer history. We're not going to go 400,000 years, but we're going to go a little bit deeper in time. And the challenge is that we've got a pretty limited window in which we actually have information on hurricanes. And we've got some information, particularly for the big ones, that goes all the way back to European settlement. But prior to the Europeans arriving on the North American shores, we have zero information about how hurricane activity has changed. And most of that record is incomplete, right? We only have an instrumental record that's maintained by the National Oceanic and Atmospheric Administration going back to 1851. And given that these events are really rare, for example, for New England event interval, we really just have the 1938 hurricane, right? It's really hard to say anything about trends, that's short of a record. And so one of the things that we've been doing is trying to come up with a different way to look at it that would expand our knowledge of them much further back in time. And what we use is geological proxies. It turns out when these hurricanes hit, they leave a very distinctive signature behind. This is Salt Pond, which is literally a kilometer from my lab at the Oceanographic Institution, which is just over here in the lab. It's a little kettle pond that eventually sea level rose and caught up to, and now has this barrier on it here. If anyone's been to Woods Hole, this is the bike path that used to be the old rail bed that went down to Woods Hole right here. There's a deep hole in the north corner of Salt Pond here that accumulates sediments really rapidly. So you can take a sediment core here, and the sediments that are accumulating there are basically a little time capsule of environmental change that's been going on at that site, going back about 2,000 years since sea level caught up to this particular pond. So what we've done is take sediment cores here, and it provides a history of a variety of things. But one of the things it provides a history of is hurricanes hitting, overtopping this beach, and transporting sand into this basin. And so here we are on the smallest vessel we have at the Oceanographic Institution. It's 2 canoes strapped together with a piece of plywood. But here's that barrier I was just pointing out. So the Atlantic Ocean is on the other side of this, and then this is that pond. And what we're doing is vibrating, using a cement vibrator, vibrating this aluminum tube down into the mud. It's like putting a straw into a milkshake, putting your thumb over the top and pulling out the straw. It's full of milkshake. In this case, it's full of mud. But that mud tells a really interesting story. And here's a photograph of a section of that mud. The dark stuff here is the mud you'd expect to find in the bottom of the pond. Really dark, organic, rich mud. These light bands are the overwash layers that were deposited when hurricanes hit. So this long core, which was about 10 meters long, over 30 feet, was able to basically give us a history of what went on here for 2,000 years. And so now we have a much broader time span to look at and sort of put the modern hurricane activity in some sort of context. And here's what basically we were able to reconstruct from that. This is modern, going back 2,000 years to 0 AD. This is the frequency of events per decade that were in that core. This first one is Hurricane Bob, which is really well represented in all the cores we took. Then there's a gap. We don't even have the 1938, 1815 storms hit so far to the west, we don't even see a record of those here. It's not until we get into the early colonial period where we have a storm in 1675 and this 1635 hurricane, the Great Colonial Hurricane recorded, and then we have all these others. The first thing that jumps out at you when you look at this is that there are intervals in the past that are far more active than anything we've experienced historically. So what that implies is that the climate system of its own accord, prior to human influence of it, is actually able to generate hurricane climates that are much more severe than anything we've experienced historically. The other thing that jumps out at you is that there's, at least thus far, no evidence of a recent uptick in activity due to the recent warming. Now that's probably just an artifact of, we just have been lucky here and haven't actually seen hurricanes since Bob. They're random at some level in terms of where they're hitting, right? So at any one location, you might have to have a long time window in order to see that sort of thing. But these really active intervals are pretty interesting, and we've sort of gone in and tried to diagnose what's going on there. And it turns out that this interval is one in which the entire eastern seaboard of the United States sees more overlap flares. No matter where we go, if it's North Carolina, if it's the Bahamas, the northern Bahamas, all of those places see lots of these event beds there. But as we get further south into the deeper tropics, you don't see them. It's really quiet at that particular interval. So it's only active along the east coast of the United States at that time. Same with the Gulf of Mexico. There's no activity in the Gulf of Mexico at the time. It's only on the eastern seaboard of the United States. It turns out we have reconstructions of what sea surface temperature was doing. And in the deep tropics, sea surface temperatures at that time are actually cooler than normal. But along the eastern seaboard of the United States, they're actually warmer. And it's actually at the onset of what we refer to as the Little Ice Age. So this really puzzled us for one. We're supposed to be going into the Little Ice Age. Suddenly we're getting lots more hurricanes. What's going on there? It turns out the Little Ice Age is defined by what's going on in Europe, right? They've seen glaciers in the Alps advance. They're seeing their crops fail because they're having exceptionally cold years. It turns out along the eastern seaboard of the United States, this onset of the Little Ice Age is actually much warmer. There's a sea surface temperature anomaly, a warm sea surface temperature anomaly there, and it appears to be driving an increase in hurricane activity. It's probably storms like Bob. And if you remember, Bob didn't form in the Cape Verdes. Bob formed off the southeast coast of the United States and then came right up the eastern seaboard. And about half the storms that impact us are of that type. They sort of form much more close to us than the storms coming off of Africa. And so our working hypothesis at the moment is that this interval is one in which the storms that are forming off the eastern seaboard of the United States are sort of getting supercharged by this warm sea surface temperature anomaly that's happening at the beginning of the Little Ice Age and coming up and hitting New England. There's a little bit of break-in activity, and then there's this interval here, which is known as the medieval warm period. Again, an interval of warmer sea surface temperatures, but this time it's actually warmer in the deep tropics as well. So here you're getting a lot more activity in places like Puerto Rico and in the Gulf of Mexico, for example. And then it gets a little quieter again, and then you have another interval of more activity, and this is another warm interval called the Roman warm period. So there's some regionality to it. Not everybody sort of gets more hurricanes all at the same time. But in each case, we're able to attribute some of this to ocean warming. Yes?
Are there a number of places where you've done something like the cores from the salt pond up down the east coast there?
Right, yeah. So there's a whole network of them. We've done some, actually some just down the road here in the ponds, and also in Mattapoisett. We've done some in New York, some in North Carolina, and a whole bunch in the Bahamas, which I'll talk about in a little bit. Other question?
So how warm does the sea surface have to be to provide the storm and force that come up the coast?
Right. So this sea surface temperature anomaly here that I'm talking about is only about a half, maybe 3/4 of a degree Celsius. It's not very much, and we've just shot past that in the last decade or so. So up until about a decade or a decade and a half ago, we were cooler than this particular interval. We are now warmer than this particular interval because of global warming. Yes.
It seems to happen every 500 years, that's which is right now.
Yeah.
Also, is there any chance those your pond was actually breached rather than just overflowing? Because
Yes.
it would change the whole
Right.
scenario if it was breached.
And the reason we actually selected this site is because that hole is actually in the northern edge of the pond. The pond next to it, Oyster Pond, the hole is right at the beach. And there the breaching is dominating. There's a lot more layers. Even nor'easters are enough at times to breach it and leave a layer. In Salt Pond, the deep hole is about 500 meters currently from where the ocean is. And so it's much less sensitive to the breaches. And we're actually able to map a couple of the breaches with ground penetrating radar. And there's at least 2 places where they've breached. But if that breaching there isn't enough. And we discovered that in Irene and Sandy. There were a couple of little breaches, the road was overtopped, but none of the sand was able to make it more than a few tens of meters into the pond. So it really requires a huge storm surge to basically make that the bottom of the ocean to transport sediment that 500 meters. So that's why we're only recording the most extreme events. They're sort of filtering out any sort of minor events or the nor'easters.
All right. That's right. Is there another question?
For the dog by the ponds down the road, what have you found for them in your mom?
We both live on the same one.
Yeah. There are lots of sand layers in them. They're much lower resolution. They're not accumulating as fast as these. But they also extend further back in time. So some of them, we have records that go back 6,000 to 7,000 years. When you get that far back in time, though, sea level has changed so much that the sensitivity of the site has changed a bit. So the short answer is that they're much more complex because of that, in terms of how to interpret them. You can't interpret the entire 7,000 years as a climate signal because the shoreline is basically moving a great distance over that time. Yeah.
Does like isostatic equilibrium come into this?
Sure, yeah. So what isostatic equilibrium is talking about the response of the crust in the mantle to the weight of the ice sheet that was here 20,000 years ago. So imagine you've got a huge ice sheet sitting on top of southeastern New England, 2 miles thick, really heavy. It's heavy enough to actually depress the Earth's crust into the mantle. And when it does that, it pushes the plastic mantle material out to the edges of the ice sheet, which causes this bulge. And then when you remove that ice, all that mantle material wants to go back and reach this equilibrium again. But it's a really slow process, and it's one that's still going on. So if you go to Hudson Bay, Canada right now, the land there is uplifted because the mantle material is still moving back, filling in where the ice sheet sat. The mantle material that Hudson Bay is getting is coming from us. So the mantle material under us is moving towards Canada, and it's causing us to subside. So not only do we have sea level rising, but the Earth literally underneath us is subsiding. We get a bonus sea level rise. It's modest, though. It's modest in relation to what's forecast in the future. So in order to get up to the amount of sea level rise that we're likely to see in the end of the 21st century, we're probably talking rates of sea level rise of 8, 9, 10 millimeters per year. The subsidence we're experiencing is something like 0.5 to 1 millimeter per year. So on sort of geological timescales, for the sorts of things that I often worry about, it sort of matters. But on sort of the societal sort of timescales, the climate part of it is much more important than the glacial isostatic. All right, so I'm going to move on to warmer climes and show you some examples of other records that we've been developing from blue holes. And in particular, I'm going to show some results from the Bahamas. And what a blue hole is, I'm going to start this video. A blue hole is a hole in the bottom of the ocean. And it effectively is an underwater cave. So when all that ice was sitting over us, it dropped sea level by over 300 feet. When it did that, in places like the Bahamas that are made out of carbonate or limestone, there was solution, erosion based from the precipitation that was going on. So this is a freshwater system. You're basically eroding the limestone and forming caves. What a blue hole is a cave where the roof is caved in, and then sea level eventually overtook it. And so it's effectively a hole in the bottom of the ocean. This is one from Abaco in the Bahamas. It's about 90 meters deep. It's really deep. The platform here is only about 2 meters deep. So again, I couldn't go in here with a large oceanographic vessel because it's too shallow. So you saw there was that little, it wasn't quite the canoe raft, but it was one made out of inflatables. But we were able to take really long cores from these blue holes, and it turns out they are really good recorders of hurricanes when they come by. I had the fortune of actually going down into a blue hole in a submarine. I'm in here. This is a blue hole on Cape South Bank, which is much deeper, so we were actually able to get an oceanographic vessel in there that had submarines, so we could actually dive into this blue hole in the submarine. Here we're descending down that limestone wall, and there are stalactites, just like you'd see in a cave today, above ground, or above the ocean. So we're then descending down this sort of sheer wall of limestone, and then as we get down to the bottom here, it's hard to see because it's kind of dark, but there's, just as we're descending on the bottom, you can see a plume of the mud spilling out in the wake of the submarine. And so this bottom is just filled with mud that's filtering down through the blue hole day in and day out. And it was, there might have been 3-4 foot seeds on the bank the day we were there, and that was plenty enough to whip up a bunch of mud from the bank, and you could just see it raining down all around us in the submarine. So that's accumulating day in, day out, but it's really fine-grained stuff. Right? It's just sort of floating down to the water column. What happens when a hurricane hits is that it whips up all sorts of debris from the bank top, much heavier, larger stuff, and dumps them into the bottom of the blue hole. And so just like those coastal ponds, it provides us a record through time of what's going on. And so this just surveyed a whole bunch of these, all through the Bahamas. And what's really nice about this, I mean, we're obviously interested in understanding what's going on in the Bahamas, but by understanding what's going on in the Bahamas, we're really understanding what's happening on the east coast of Florida, as well as the east coast of the United States. These are really well positioned to sort of catch the storms just before they come and impact the U.S. mainland. So each one of these stars is one of these blue holes from which we've got one of these long sediment cores. So here we are. We just landed this immense core. This is a 60-foot long continuous core that was just pulled out of the bottom of one of these blue holes. And it's accumulating really rapidly, and I'll show, I think, the next thing. Here's what the sediment looks like. There's sort of this chalky gray sediment. That's the stuff that sort of I saw raining down around me in the submarine. What happens during a hurricane is you get this sort of debris layer, all sorts of coarse debris that's knocked into the pond. Of course, the next step is we need to figure out when those happen, right? It's sort of, oh yeah, there's a bunch of storms, but if we don't know when they happen, we can't really say very much about what it means. And the way we sort of develop that chronology is largely based on radiocarbon dating. And what this is the radiocarbon history that we've been able to put together. So it's going back about 18 meters on this axis, and this is time on this axis. And what happened was this thing is surrounded by all these mangroves. And little mangrove leaves would come in and, along with the mud, filter down into the sediment. We'd find these in the core, and we could, using radioactive decay of radiocarbon, which decays at a fixed rate, we can basically figure out how old that leaf was and how old that sediment was. And here's that trajectory. So we basically know a chronology for this core and know fairly precisely within a couple of decades when this particular event occurred. And that's what it looks like. It's great, isn't it? What you're looking at here, so this is time, again, modern on this side, going back about 1,500 years. So that entire 60-foot long core only represents 1,500 years worth of time because the accumulation rate is so high. The red is when we take that really long core, the first thing we have to do when we get to the surface, because we can't get it up over our heads, is we have to bring it horizontal. So the goopy stuff at the top of the core gets mixed up. So we have to take a replicate, shorter core to sort of capture that surface. And so the red is the replicate that overlaps with the longer core. So just to sort of put it in perspective, here's the American Revolution in our core. Here's the Pilgrims. Here's Columbus. All of this is pre-European history in North America, right? And our record goes back all the way back to the fall of the Roman Empire. So we now know, at least for the southern Andros Island, the number of times they were hit by hurricanes are going all the way back to the fall of the Roman Empire. We also have some known historic events. The first event that's preserved in this core dates to 1945, and there's another one in 1919. The one in 1945 goes on to hit Miami 6 hours later. And there's actually newsreel film of this hurricane hitting Miami, which is, at least for me, I usually don't get to see the hurricane. It looks like I'm looking at the event beds in the court. But to have, you know, a newsreel film of the hurricane hitting just a few hours later is pretty cool. This one goes on, this one intensifies in 1945 from a Cat 3 to Cat 4 before it hits Miami. This one intensifies to a Category 4 and then eventually goes on to hit the Gulf Coast. So this is obviously work in progress. We've got lots of these sites going on. Our goal is to reconstruct what the entire basin is doing through time for as long back as we can possibly do it. You know, this is a map of all the tracks that we know of in that NOAA data set that I talked about, that instrumental record that goes back to 1851. And all of these dots are sites that are in varying stages of completion. Some of them are complete and already published, others are sort of in progress, and others we've just collected the sediment cores for. But the idea is that we're trying to build this large network to basically reconstruct what's going on in the entire basin. And we've also expanded this work into the Pacific as well. If you look at a snapshot of some of the higher resolution ones we have, the top one is here at Salt Pond, the one I showed you earlier. There's that active interval from about 1400 to 1675. This is that record I just showed you from South Andros, and then this is the record from Mullet Pond that's up here in the Gulf Coast of Florida. And there's lots of different things going on here, but one of the things that's going on, in all three of these records, most of the rest of the last 2 millennia is much more active than anything you've experienced historically. Which again, at least to me, is pretty frightening. That it doesn't even, the climate system doesn't even need us turning the knobs. Of its own accord, it can generate hurricane activity like we haven't seen before. But there's also these regional differences. Here, for example, South Andros in the Bahamas looks a lot like what's going on in the Gulf Coast, where it's pretty active all the way through the first millennium up to about 1400 years ago, and then it gets pretty quiet. Right when those two records get quiet, the East Coast gets really active with this active interval that includes that 1635 Great Colonial Hurricane we talked about. Okay, so I'm going to sum it up here. Sort of hoping to cut it a little short so we have time for discussion. First summary point is that sea level is currently rising at a rate we haven't seen in at least 6,000 years, since there was ice sheets here actively melting. And we expect it to rise several more feet by 2100, and perhaps even tens of feet by 2500 CE, but again, I'm not going to worry about it. Most modeling studies indicate we should expect more frequent intense hurricanes, but there's a lot of geographic variability, a lot of variability between models, and the uncertainty is pretty high. So I'd say we're not very good at the moment of specifically forecasting what we might expect in the very near future. That said, the paleo records, these long-term reconstructions, suggest that the climate system before human interference was capable of producing intervals of heightened hurricane activity. And in many cases, those levels of activity were much more active than anything we've experienced historically. And this is a point I always like to make because, so there's lots of debate. We're not quite sure. We know sea level's rising, and it's very, very likely to keep rising, probably much faster. The hurricanes are a lot more uncertain. But that doesn't mean we shouldn't act. We don't, the negative impacts of any future hurricane activity are going to be greatly exacerbated by this continuing sea level rise, whether or not we see increases in the hurricane climate. We don't need to invent some doomsday scenario. All we need to do is have a 1635 hurricane come back today, and we're in big trouble, right? And largely that's because of this coastal population growth part of the equation. And I try to end on a good note. It's sort of a doom and gloom, I know. The good news is that we have many tools to mitigate the impacts of hurricanes, and they no longer take us by surprise. It wasn't that long ago we had no idea they were coming. In 1938, all the forecasts, there wasn't National Weather Service at the time, all the forecasts said, oh, that's going out to sea, don't worry about it. And of course, they made a direct landfall. We're doing a much better job forecasting, particularly the tracks. It's astonishing. If you remember back to Sandy, it was like a week in advance we knew the track that Sandy was going to take. And it wasn't a sort of regular track. It was that very unusual track where it went, took this recurve into the New Jersey shore. So we're doing a really good job with tracks, largely. Intensity, it's a little touch and go, and largely that's because we don't understand what's going on in the upper ocean. These hurricanes are getting their power from the heat content of the upper ocean. We're really good at measuring the sea surface temperature with satellites. We can measure the skin temperature, but we don't know what's happening in the water column. And that's really important because a hurricane, particularly an intense one, can mix up the water column, cool it, bring upwell water from below, and basically shut itself down. But if there's a really deep well of warm water, it can, has an unlimited source of energy and can really intensify. So it's really critical that we understand that. And it's the reason we don't do nearly as well with the intensity forecast as we do with the track forecast. And then the other part of this is obviously our capacity for communication. I mean, it's almost annoying, right? I mean, we know, like, we're getting beat over. Anytime there's a hurricane out there, it's just on the news and it's beating us over the head. But that's great, because we all know it's out there. Hopefully we take the necessary precautions. Thank you. I've listed a few interesting further reading that are largely focused on historic hurricanes, including the 1938 hurricane, if you're interested in reading more. But I'm happy to take questions.
Saving lives. Nothing can be done really to prevent the property damage.
I mean, that's
coastal erosion.
That's clearly the first priority, right? I mean, we've done some foolish things, right? We've built in places we probably had no business building in. So I think the first priority is obvious. Let's make sure we can get people out of harm's way. You probably have insurance. We can buy new stuff. But let's make sure we get people out of harm's way. Of course, if these forecasts are right and we get many more Cat 4 or 5 hurricanes, insurance might be pretty hard to get to later on down the road. But as a first order, we certainly want to start preparing to get people out of harm's way. And it's pretty frightening, actually, because we did a pretty poor job in Katrina, for example. We had pretty good forecasts. We had several days to get people out of harm's way in Katrina, and we didn't do a very good job. In the Northeast, the intense storms that hit us, like 1635, 1938, 1815, they tend to be moving really rapidly. Storms tend to accelerate as they move up into northern latitudes. The ones that are moving really fast, that are intense and moving really fast, are the ones we really have to worry about, because as soon as a storm leaves the Gulf Stream and gets over colder water, it starts to shut down. So if you have a slow-moving intense storm, you can go from a Category 4 storm to a tropical storm in a few hours, or at least a day or so, right? But if it's moving really rapidly, it can still hit us at a strong Category 3 or perhaps even a Category 4. And that's what happened with these historic storms. Some of them, like 1938, Carol, they're moving at like 40 or 50 miles an hour. The way that plays out in terms of timetable is pretty scary. So you've got 1938 makes it from off Hatteras to us in 8 hours. So we don't have the 3 days that New Orleans had. We have a fraction of a day. So that poses some immense challenges. And particularly since we've got an enormous population, right? You imagine, so play the scenario out in your head, right? Where we've got a Category 4 storm sitting off of Hatteras. The Weather Channel's got the cone of uncertainty that goes from somewhere from New York to Boston. And you've got 12 hours, right? So how do you deal with that? How do you who do you evacuate and how do you handle that? So that's clearly the first priority. I don't have a lot of faith in how we sort of deal with our stuff. I mean, we have a bad track record, right? I mean, as a graduate student working on this stuff, I kept thinking, well, society's going to get this as soon as New Orleans gets hit, right? Once we get hit, get demolished, we'll figure it out. So Katrina happens, and all we did was we just rebuilt New Orleans, right? And thought, well, New York. New York gets it, they'll figure it out. So then we get Sandy, which was a fairly minor event, devastates New York and New Jersey. The first thing we did was rebuild the Jersey Shore. So we have some really bad instincts, right, that we'll have to try to overcome. And I don't think we're in a position where we're going to be able to with policy, really legislate this and solve it pre-storm. We just don't. It's just hard. You can't go down to this neighborhood, all right, I've decided you guys are too low, everybody out, sort of thing, right? But we have opportunities when the storm hits, right? So when you get something like Sandy, when you get 1938 hurricane sort of comes back, right? There's going to be massive destruction. That's the time to start thinking, right? Okay, what's the smart way to sort of go about in the future? How do we rebuild and try to be more resilient rather than just rebuilding right where we were? The problem is, at least in the past, the events have been rare enough that they can sort of dismiss it as, oh, it's a one-off, that's not likely to happen again. But if these forecasts are right, rather than happening sort of once in a generation or once every 2 generations, it can happen multiple times in a generation, which obviously poses the big risk for us. Yes?
2 quick questions. One, why the disproportionate sea level rise in Narragansett Bay? It's been like 10 inches since 1930. And also with respect to mitigation, do you think things like the Billion Restore Project in New York City will have any kind of impact on the next one?
Okay. The sea level, the extra sea level rise in Narragansett Bay is due to that isostatic stuff we remember earlier. So you're getting subsidence going on, so sort of you're getting bonus sea level rise. So all along southern New England is the part of they call the peripheral bulge, that part of the planet that is sort of bulged up by this extra mantle material. All of that is sort of subsiding. So all the way from New Jersey to Cape Cod is subsiding. The hinge point is somewhere close to the Maine border. When you get to Maine, it's sort of neutral. And then when you get to the Hudson Bay, it's uplifting. What was the other point?
The mitigation of like Billion Restore Project.
Oh, that was
will
true.
that have an impact?
So we actually did a study on the impacts of oyster beds there. And effectively, what we did is assume, we had some maps of what the healthy oyster beds looked like when the Europeans settled. And we basically said, okay, let's go back to 1620 and assume we have those oyster beds again and run simulations of some of these historic storms. And basically what happens is that there's zero impact on surge. You still get just as much surge. But what those oyster reefs do is they cut the waves down. So surge is just the rise, the sort of longer timescale rise in water level that's being pushed up on shore by the onshore winds, and a small effect from the low atmospheric pressure of the storm itself. Superimposed on top of that, you have the wind-driven waves. And so what those oyster beds are doing is sort of causing those waves to break offshore. And so in that sense, it's sort of going to mitigate some of the impacts on shore, but it's not going to prevent you from getting less wet in terms of storm surge. Yes, sir.
From what you're saying, global warming, even with our best efforts, is going to continue. Mm-hmm. And even if, we all went back to, say, sackcloth and ashes, the developing countries aren't going to stop. So, we're just stuck with it permanently.
That's the pessimistic view. Yeah. Unless there's some way to transform both our economy and these other economies to something that's not greenhouse gas emissions, that's the road we're going down. So there's lots of emphasis on mitigating those, and I think that's great to do. I drive a hybrid. It's a big hybrid, but I got kids in baseball gear to cart around, so we can do those things and make our best effort. But as I was pointing out earlier on, even if we're able to do this, this is something we're going to have to live with. And so it's not just drive your hybrid and try to reduce your carbon footprint, which you surely should do. But we're going to have to learn to live with this, even if we manage to sort of reduce our emissions. Sorry.
What does a 3-foot storm surge look like? Does that just mean that the water's going to be 3 feet deep, so many miles inland?
Right.
I mean, much depends on whether there's a storm behind it.
Right.
What do you think? They look weight of water. Right.
They look
it just
different.
Everything is fat.
Right. Let me see if I can find the figure because I can show you some actual data. It varies from storm to storm. Sandy, for example, was very slow moving. And let's see, I got way too many slides here. And so the storm surge from Sandy played out over much more than a day. Somewhere here. I told you I had to slide. I knew questions would come up.
The whole thing is going to be the surge as it keeps pushing forward. The way the water, the southern waves,
Here.
it's actually like the tsunami. You keep pushing more water in.
Okay.
The waves keep pushing more water.
We watched that.
Ah, very good. What's on the left is a simulation of the 1821 hurricane. So it's the last really intense hurricane to hit New York. It's also a Category 3 storm. It hits on September 3rd, 1821, which is the first Monday in September. If they had celebrated Labor Day back then, it would have been Labor Day. You can imagine a Category 3 hurricane blowing up the Jersey Shore on Labor Day. The observations in the lower Manhattan were that the storm tide rose 14 feet in an hour. So in this particular event, you had a really intense storm moving very rapidly, you had a very rapid increase in water level, followed by a dramatic fall as the wind direction shifts as the storm passes. Sandy was a very different story. So this is the actual predicted tide in red for that day in 1821, and the yellow is the model tide in this case that matches those historic reconstructions. Here is the observed water level rise in Sandy in lower Manhattan versus what was predicted. So in this case, because Sandy was so large and so slow moving, that the storm surge event actually lasted much longer than a day. Unfortunately, we were very unlucky in Sandy in that the peak of the storm hit it right at high tide. In 1821, they were really fortunate and the peak of the storm hit at dead low tide. So, you know, this was greatly accentuated by the tide that actually happened to hit on in the case of Sandy. Of course, what was going, Sandy hit this urban population all up and down the eastern seaboard. 1821 obviously hit Manhattan, but the Jersey Shore at that time was a bunch of fishing shacks and salt works, right? There weren't things like Atlantic City. So they hit it very different coastline, basically. Yes, sir?
Talk about political will and what would that look like if we did our best?
What's frightening to me, unfortunately that study I showed that just looked at the Cat 4 and 5 hurricanes for the scenario in which we do something. They didn't also do that for the scenario in which we don't do something, right? And I think knowing that difference, right, so that's what we sort of gain by actually driving our hybrids and trying to reduce our carbon footprint. My suspicion is that if they were to do that, there would be a substantial difference between, we get a lot of bonus Cat 4 and 5 hurricanes by going that extra several degrees of warming. That work hasn't been done that, so I can't say that for sure, but that's my suspicion. But that's really what we're preventing. So instead of, it's not as though we're going to prevent hurricane strikes by driving our hybrids or whatnot, but it might be the difference between having one a decade versus two a decade, something like that. Yeah.
So this may not be in the science realm, but I understand with Katrina and maybe the emotional, political, resilient, rebuild thing. But from the perspective of insurance companies that are going to make money, what drives them to allow all the rebuilding around like that?
So some of this early work was actually funded by the reinsurance industry. And really the genesis of this reconstruction work was motivated by them. I was a graduate student at Brown. They approached us. They had just been burned by Andrew. They had a catastrophic hurricane strike in South Florida. A lot more losses than they expected. They realized, so the reinsurance industry, the people that are insuring the insurance companies, they realized that they didn't have very good statistics for these really intense but really rare events. And so they came to us and said, could you use your sediments to sort of reconstruct storm history? And I said, probably not, it's never going to work. 25 years later, it's basically what I'm spending my entire life doing. It turned out, so as part of that exercise, so they funded a lot of the initial work where we were able to actually show that you could do this. And every year they would invite me to Bermuda to sort of present this. The home of this initiative was in Bermuda, where a lot of these companies are based. And they would politely listen to me for 45 minutes. Right? I'd give them a talk like this, and they'd just sit there with a pad of paper. All they really wanted to know is what's the number for New York, so I can go home and plug it into my wrist model and figure out how in trouble I am, basically. But one of the things I learned from those interactions with the reinsurance industry was that hurricanes are good for business. They're worried about getting too many really big ones, obviously. But one of the things that hurricane strikes cause us to do is go out and buy insurance. So as long as they don't occur too frequently, it's really good for business. And another perspective on that, which I just learned.
And then it's the volume sales.
Right. And one of the other things that I learned recently from, I was at an event in South Carolina last year, and we had a very nice dinner after, and I was chatting with folks, and I was really surprised to hear their perspective about Hurricane Hugo. So Hurricane Hugo blasted through Charleston in 1989, and they thought, what a great thing Hugo was. And I was like, how so, right? It basically, for them, was a huge influx of insurance money. It was urban renewal, right? So as if they occurred just every once in a while, some people can perceive them as a good thing. Our problem is here that we're talking about them occurring much more frequently, and if the insurance market collapses, we're all in trouble. Yeah?
So we're seeing a $20 billion in debt, and there's probably similar about it not even existing in the future.
Right.
And a lot of people aren't going to get that insurance.
Right, right. So one of the things that we've done over the later half of the 20th century is to subsidize building in the coastal zone. So the federal flood insurance program, for example, is subsidizing, so our taxpayer dollars are subsidizing people being able to get insurance in the coastal zone. And so in that, we're able to actually encourage building in places that we probably never should have built. And then even beyond that, we have FEMA who comes in post-storm and has traditionally bailed communities out. If that system fails and the federal flood insurance system fails, we're at the mercy of the insurance companies, which will be fine provided that we don't get too many events and they completely go under, or just the rates are so high that no one can afford it. Yeah.
Is there similar information, for example, from the west coast of Europe or from the west coast of the United States that you could make these comparisons?
In terms of the hurricane sort of thing, there are some reconstructions of storms from Europe. They don't typically get hurricanes, though some of these storms maintain their intensity long enough they eventually go on and impact Earth, just as non-tropical cyclones. Most of our other work has been from other tropical cyclone-prone regions, like the western North Pacific and the South Pacific. So we've got a lot of work going on in the South Pacific, in Fiji and Vanuatu. We've done work in the Marshall Islands. We've done work in French Polynesia. And so we're sort of the work started in the western North Atlantic, largely driven by the reinsurance industry, who was really worried about New Jersey, New York, that sort of thing. But that's it. We sort of creeping out, trying to get a more global picture. So that's what I have to do for the next 25, 30 years until retirement. Yes, ma'am.
Glenn, can you talk about how your work is done? There's not all
Right, right. So it's a mixed bag. So initially, as I said, it's pretty unusual that industry sort of stepped up, realized they had a problem that they thought some basic scientists could sort of figure out. Somebody was sort of looking at sort of fundamental research, and so they sort of kick-started it. And after we got to the point where they would politely listen to me for 45 minutes waiting for the number, I kept telling them after I gave them the number, but don't believe that number because the boundary conditions have changed. They basically wanted me to get a 1,000-year or 2,000-year history from New York, tell them what the number was, and they run off with the risk model. The problem is the climate's changing, and the risk of hurricanes isn't stationary, it's changing through time. And so I beat on them for several years about that, and they just weren't interested. But all those are fascinating questions that certainly needed answering. And so that opened up federal funding. So much of the work post that initial funding that got it started was funded by the National Science Foundation. Some of it was funded by the National Oceanic and Atmospheric Administration, and some of it was even funded by the Defense Department. In particular, some of the work in the Pacific has been funded by the Department of Defense. So for example, they built the Reagan missile defense system on Kwajalein Atoll. It's a $4 billion facility. It's sitting on a little mound of gravel at 2 meters above sea level. Right? So they sort of realized we need to know a little bit more about how that might be fair in the future, and so they funded some of that work. So it's sort of a mixed bag of various federal agencies, but all of them tend to be pretty conservative. It's sort of hard to get sort of new stuff funded there. So one of the things that's been really important over the years is donations from foundations and even individuals who are sort of interested in the science. This little seed money allows us to go some new direction that is far too provocative for the National Science Foundation, but allows us to sort of move the ball down the road significantly. So it's sort of a mixed bag of, you know, the federal agencies, foundations, private donors. Yes?
Two questions, one easy. What's the elevation of Woods Hole where you all live?
It varies considerably. We're on the moraine where the ice sheet rested for a few thousand years as it retreated. So much of the Oceanographic Institution, including my office, is about 45, 50 feet above sea level. Okay. So we're in pretty good shape. Our dock facility, though, not so much. So and it's a dock facility that, you know, had a 50-year life, and we're in year 70 sort of thing. So we're in the process of trying to figure out what to do about that, but also wrestling with all these issues in terms of sea level rise and how do we sort of build something that's going to be resilient for the next one.
The second one's a little harder. Have you correlated the variations with our planet to the sun, sunspots, things like that, how our orbits are getting closer to Earth and further times?
Right.
Is that correlated to hurricanes? That's
right. So a lot of our climate change that the Earth has experienced over long time scales is actually driven by very subtle changes in our orbit relative to the sun and the inclination of our axis of spin and things like that. That's what gives us those ice ages and interglacials. So you know, it can change the balance of energy getting to the Earth enough that you can actually grow large ice sheets. Those are happening on pretty long time scales, largely, you know, tens of thousands of years. There are very small variations in just the solar output of the sun.
The sunspot.
Right. And that's been a very active area of research for quite some time. And the challenge is, you know, people have tried to relate the varying output of the sun's energy with the climate that we've experienced, or the change in climate we've experienced. But there's such small changes that none of the models can sort of capture it, right? We have to have some way to sort of magnify the impact of that. And there are some mechanisms out there. For example, if you can have just slight changes, if you can increase sea ice, right? Sea ice bounces a lot of the energy back and it can allow you to go into more cool conditions. But over the last, say, 10 or 20 years, much of the research is pointing towards that solar activity just not being enough to trip the system. In conjunction with other things, it might be enough. In particular, if you have solar variations with volcanics going on, you can drive some cooling. And that's one of the leading theories for what drives that little ice age in Europe. At least the theory I think is most likely to prevail. Probably a very small component could be the solar output, but what happens with the volcanism, so right at the beginning of this little ice age period, there are a whole series of massive eruptions. They only cool the planet for a few years at most. But what happens when they cool the planet for a few years, they allow sea ice to expand in the northern latitudes. And when it does that, it decreases the albedo, you know, increases the albedo and collects more sunlight. But it also, you know, so it's this feedback mechanism in which you can persist a cool event longer. And that's probably something like what's going on with that area. Nothing, so you know, we have some understanding of sort of how things like that have sort of driven climate change over the last several millennia, and even longer on these sort of glacial and interglacial scales. And we incorporate all that into the climate modeling. And when you put all that into the climate modeling, we should actually be cooling right now. We should be inexorably sliding into the next ice age, right? Exactly. So, you know, if you're a proponent of global warming, there's your argument, right? Who wants to go into the next ice age, right? We're preventing that. But obviously, there are all these other impacts that are going to be probably far worse. Yes?
And, this is a non-scientific question, but I wonder if there's any archaeological folkloric information about how Native peoples in North America dealt with these big storms.
I heard the Narragansett, I haven't actually talked to a Narragansett. I talked to someone at a meeting, an archaeologist studying the Narragansett, who apparently have a fable about the water coming in and how they all have to get out of the way of the water when it comes in periodically, which they were sort of interpreting as probably this sort of hurricane event where it comes in and inundates vast swaths of the coast. But unfortunately, much of that stuff is lost, right, to our Yes?
Meaning you did my decision a couple years ago to buy a property here in Newport, but my question is, scenarios that I've seen in terms of, category 4 or 5, we're in it, and also the sea level rise. And, where my little house is, I'm okay, which is great. But then I also read stories, and I'm wondering if they're accurate or not, that our current hurricane category scale is not sufficient anymore, if some of these scenarios come true.
Yeah.
And, what should we look for, what should we cost?
Our current system is horrible. It doesn't accurately capture the real risk, but it's so ingrained in the public conscious that we're never going to go away from the Saffir-Simpson scale, I don't think. The reason it's not that reasonable scale to assess impacts is because all the Saffir-Simpson scale worries about is the maximum sustained winds. It doesn't take into account the trajectory of the storm, the coastal landforms it's hitting, or importantly, the size of the storm. So one of the intense hurricane strikes that I didn't mention was in 1869. We actually had two storms in 1869. There was a Category 3 storm that hit right at the Rhode Island-Connecticut border, and there was a second one that went right across Cape Cod, very similar to the 1954 season where we had Carol and then Edna. But the reason I haven't highlighted that 1869 storm, it was very intense, but it was very small. And it was very fast moving, and it had a devastating impact in a very small area, but it didn't have a very widespread storm surge because of its geometry. So today, that would have been categorized as a Category 3, but its impacts would have been much more limited to these other Category 3s that were much larger and caused much more widespread damage.
Yeah, do you want to take one more question?
Sure, one more. Who's got a good one? Sure.
I don't know if this is a question or a comment. We'll find out, I think. I think this has been great. I'd like to thank you and thank the host too and so forth. I wonder if we can figure out a way for us to continue the conversation. There are a lot of people in this room whom I do not know who have some very good ideas. I can learn something from them. Maybe we can all learn from each other.
Right.
I think that would be a very good outcome from this particular meeting. And I wonder, is it the Historical Society or the Restoration Foundation? Who's going to help us on that? Maybe it's Hugo.
Right.
I mean, you have a membership list, I'm sure.
Right. And I try to do these sort of events fairly regularly, so try to get the word out. But that dialogue is really important. I can live in my ivory tower, work in my computer models, do my thing, publish a paper every once in a while. But the results are relevant, and if you guys don't go out and read my papers, you're not going to know, right? So I think hopefully this is the start of a dialogue.